Hello friends, in this video we are going to deal with a PBL topic, that is a project based learning topic that was undertaken by the first year engineering students of the academic year 2018-2019. The name of this particular topic is determination of the elastic constants of a polymer using light interference in wedge shaped air film, and the polymer that we are going to deal with in this particular case is that of a globe that we normally use, the surgical gloves that we normally use. So let us see the different kind of principles that we are using in finding out the Young's modulus and the Poisson's ratio of this particular material. First of all, let us start with the objectives. The objectives of this particular study are to determine the thickness of the polymer material, that is the surgical glove, using the fringe width of an interference pattern formed in a wedge-shaped air film. That is basically we are dealing with an optical interferometer. And the second objective is we are using this particular values to calculate the Young's modulus and the Poisson's ratio of the polymer material using the thickness value. Here is the first experimental setup that we are going to use in order to find out the values of Y and nu. And this is basically an optical interferometer that is formed with the help of two glass slides. Now in this particular glass slides, what we are doing is we are having two glass slides, something like this, and in between this I am having the polymer strip. This distance is very small. One can say that this is the angle alpha out over here, and it turns out that this particular value alpha is equal to lambda upon 2 mu into x, wherein lambda is the wavelength that I am using in order to generate the interference pattern. Mu is the refractive index of the medium that is present over here, which is normally air that we have taken, and this is the polymer that we are dealing with, whose thickness we wish to find out. So in this way, you are actually going to get your alpha. The minute you are going to get alpha, you are going to take the tan of this particular value, and as you know that your tan is going to be this distance, which is going to be equal to L, right, and this distance, the ratio of this, that is the ratio of the opposite side, which is T, divided by this distance, which is equal to L. And as it is obvious from here that your T, that is the thickness that we require for the polymer, is equal to L into tan of alpha, and thus we can determine the thickness of the polymer. So this is the equation that we are going to use. The next question is, how do I determine the thickness, or rather how do I determine the values that are present in this particular equation? X in this particular case is nothing but the fringe width. This is the fringe width which is there of the interference pattern. As it is obvious from here that if your fringe width is less, this means your alpha is more, and if your fringe width is more, this means your alpha is less. Both of them are actually inversely proportional to each other. So using this particular basic light interferometer, we simply constructed this in our lab, and the light, the lambda that we used is nothing but the sodium light, that is 5893 angstroms, and we are simply using two glass plates placed one above the other, and we are introducing the polymer, that is in this particular case we are actually using the hand glove material in between these two in order to create this wedge. And as you can see from this particular figure out over here, that we are having, in this particular case, we are having a particular interference pattern, and in this case you are having another interference pattern. One of them is going to be the loaded one, and another one is going to be the unloaded one. So this is going to be the unloaded one, and this is going to be the loaded one. Now as you can see from here that the fringe width over here is more and the fringe width out over here is less, because this fringe width is taken when this particular element is not subjected to any force, and this is taken when it is actually stretched, and that's the reason why, since its thickness decreases, the fringe width which is there is actually increasing in this case, right? And based on this particular data, we substitute those particular values in this particular equation, minding that the value of lambda is 5893 angstroms, and using this expression we find out the value for alpha and hence the value of the thickness of the polymer under the stretched and under the unstretched, or rather it is the other way around, under the unstretched and later on followed by the stretched condition. So this is the basic principle in which our optical interferometer works. In the second measurement that we have done over here, there is nothing but an optical extensometer. Now in this optical extensometer, or rather to be more specific, since we are using a microscope in this particular case, a microscope extensometer. So we are actually taking the same material and we are subjecting it to a force. So this is the stretched material out over here, and down we are actually subjecting it to a particular load which is there. And then the extension of this particular strip is actually measured with the help of a microscope. Now mind you students, in this particular case, we are actually measuring the extension in two ways. First of all, the axial, that is the direction in which your load is being suspended, and also lateral. So it is something like this that we are actually going to see. So if at all the unstretched material is something like this, and then let us assume that the stretched material will be something like this, and definitely you will agree with me that this will become something like this out over here due to the stretching here. So this was your original length, and this is going to be your stretching out over here. From the axial way, there is delta L. Initially this rather I will say is the final reading out over here. Let us say that was your T dash, and previously, since I cannot mark it over here, and previously this is nothing but, let us say it is T. So T minus T dash. So this is something which I am going to do. So that is T minus of T dash divided by the original one, which is nothing but T. This divided by your L minus of L dash, and this L dash actually takes into consideration L plus delta L, and this divided by your original length, which is nothing but equal to L. Now what is this ratio that we have actually done over here? This is nothing but your lateral strain divided by your axial strain, and this is nothing but your Poisson's ratio. So this is one way of finding out the Poisson's ratio. Let us go a little bit back, and you must have remembered me telling you that we have actually found out the difference in the thickness because of the fringes. Now in that case also we have actually considered the difference in the thickness, but mind you, in that particular case the difference in the thickness is, so let us assume that this material is something like this. So in the first case we measured the change in this thickness, and in the second case we measured the change in this thickness, and both of them will actually yield you values of the Poisson's ratio, because both of them are actually perpendicular to the axial strain, or rather to the axial extension. So these are two different ways in which we have calculated Poisson's ratio. So the change in these dimensions, which is actually of the order of micrometers, was done with the help of an optical interferometer, and the change in this dimension, since it is observable by a microscope, this particular change was measured with the help of an optical microscope. So that's the way that we have actually done the difference between the two, and in both the cases we have yielded, or rather we have found out the value of the Poisson's ratio. So as it is here, we are subjecting it to the load out over here, and we have the microscope besides it, and that actually measures this particular change that we have. So up till now, we have actually obtained the values of the Young's modulus, or rather we have studied the experimental procedure for obtaining the values of the Young's modulus and the Poisson's ratio by using the optical interferometer and using the microscope extensometer. So what are the different ways in which we have done it? These are basically our pure lab methods that we are utilizing. So for example, let us assume that this is our sample out over here, and we are actually, in one method, we are measuring the change in this particular thickness by the optical interferometer method, and in the second case, and of course the elongation, and in the second case, we are determining the values of this change, the change in this due to stretching and the change in this. And both of them, as you see, this as well as this, and this one as well as this one, both of them are perpendicular to each other, and hence they can be used to find out the changes in these particular extensions can be used to find out the Poisson's ratio. So now, the next thing is, we have got a values, we definitely need to test it with a particular standard, and with this particular objective, we approached one particular institution, or rather a lab, which was in MIDC, which is very close to our college, and this particular lab provided us with the values for Y only. They could not find out the values for sigma. So what was the method that we used? Let us study that first. So the method that we used for that was, we have the sample that is being placed out over here. So here is actually the sample which is over here, right over here, we have the sample that is placed and that is being stretched, right? And over here, what we have is nothing but a kind of sensor that actually, since we are actually pulling it, this particular sensor will tell us the force with which we are actually pulling it. So the force to which the particular sample is being subjected. In our rudimentary, or in our version of the lab, we knew the weights. So in this particular weights, let us say if the weight is of 50 grams, we simply multiply that by 9.8, and that particular value will give you the amount of force to which it is being subjected. But in that particular case, this was not a very continuous increment. Here we are having a sensor that is actually increasing the force on this particular sample in an incremental way, this way, and it measures it in each and every step that way. So that's the only difference. But there is one more difference in this particular method. What we are doing is, to this particular sample which is sprayed, we are actually spray painting it. So for example, let us say this is the particular sample that we are actually dealing with out over here. We are spray painting it, and due to the spray painting, what happens is there are some dots. And when this is getting stretched, there is a video that is being kept in front of it, and hence it is called as a video extensometer. And this particular video actually records, you can see the screen out over there. So for example, you can see the output of over here. This records the changes between the dots, both in the lateral way and in the axial way, and it takes this particular value to determine the values of your Young's modulus. So this particular value is more of, one can say, with a better approach and with a better least count, and that's the reason why we took that as a particular standard to compare the values actually that we obtained. Now it is time to just take a look at the different kind of results that we have done. And the results, the very first results we are going to discuss is that of nothing but of the optical interferometer. So in the first case, you will see that on the very first column, the header of that is parameters followed by unloaded. This means what is the values when no load is being given, followed by the loaded force, which is equal to 0.05. Since we have attached a weight of 50 grams, that's the reason why it is 0.05 kg, multiplied by 9.8, which is the acceleration due to gravity, and that works out approximately to 0.49. Prior to doing this particular calculations, let us do a quick revision of what is our Y. That is nothing but the Young's modulus, and your Young's modulus is nothing but is equal to the force upon the cross-sectional area divided by the delta L, which is the change in the axial length divided by your L. So this is how actually we are trying to find, we will be finding out the Young's modulus. Once again, there are two cases in this one. There are two cases for finding out the Young's modulus. Now, how did I find out the Young's modulus? In the case of the optical interferometer that we are going to discuss out over here, right? First of all, I kept the slip something like this, right, without being subjected to any force. So the force that is being there, I will say the weight to which it was actually being subjected was actually equal to 0. But the minute I am subjecting it to particular force, this will become thin, something like this, and your weight in this particular case is equal to 0.05 multiplied by 9.8. So as you can see, this particular change is reflecting in the value of your x, because I know what is the value of my x in this case. So let us say this is x and this is going to be your x dash. So from both of these values, I will be able to find out what is the change in my thickness. But for this particular case, I will be requiring this thickness because I have already subjected it to a force. So this is the unstretched version. This I will be requiring it for calculating the Poisson's ratio. So in this particular case, I will subject the force F out over here. The cross-sectional area will be obtained in this particular way. Now since I know the value of the thickness in this particular case, the value of the thickness of the rubber polymer comes out to be 114 microns. So this means the cross-sectional area, I am drawing it in a different way. The front view of this one, So this is turning out to be, 114 micrometer. And this we had kept it as a standard of 1 centimeter. So when I multiply this two, I will get my cross-sectional area out over here. So I know the force, I know my cross-sectional area. Now the delta L, we simply used a ruler. The value is given out over here. The length initially, the unstretched length was initially, it was 9 centimeter. And when I subjected it to a force of 0.49 Newton, then in that particular case, the new length was 17 centimeters. So I find out delta L in that case. That delta L I substitute it out over here, divided by the unstretched length, that is nothing but 9 centimeter, and that's how I get the value of my Young's modulus. And this of course turns out to be 6.62 into 10 raised to minus 4 gigapascal. So this is the way that we are getting the values. Now the next thing, how do I find out the Poisson's ratio, nu? In the Poisson's ratio, we already learned about the definition out over here. So in this case, for the Poisson's ratio, right, we are measuring the difference in the thickness, in this particular thickness out over here. And this particular difference, right, that is equal to delta T divided by the original T. This means delta T is what? 253 micron minus 114 micron. That's the value of your delta T. And what is your T? Your unstretched thickness. There is nothing but 253 micron. That will come out over here. And this I will divide it by delta L divided by L. Delta L in this case will be equal to 17 minus 9, which comes out to be 8, divided by L, which is nothing but 9 centimeters. So when I take this particular ratio, the value of nu that I obtained out over here is coming out to be plus 0.488. Since it is a ratio, it will not have any units out over here. And this value, as it turns out from there, is coming out to be 6.62 into 10 raised to minus 4 GPa. Now students, I have a question out over here, and the question out over here is this: delta T is actually decreasing, but delta L is actually increasing. So in a way, I shall say that your final length is more than your initial length. So this value will become negative. Whereas in this particular case, your final thickness is less than your original thickness. This will stay actually positive. So eventually, because of this negative delta L, you will get a negative value. But as it so happens that by definition itself, I am putting a negative value initially in this case, and hence due to all this, this turns out to be a positive value. So this thing has to be noted. So hence it is plus 0.488, and that's the value of your Poisson's ratio that we are obtaining for this particular sample using the optical interferometer method. So we have up till now obtained the value of y and the value of nu using the optical interferometer method. Now what we are going to do is we are actually going to obtain once again the value of y and the value of nu using the microscope extensometer. So in this case what happens is, as we already done it, already told to you before, so in the case of the microscope, we have measured change in this. Let me put it the other way around. In the case of the optical interferometer, we have measured the change in this thickness. Now we are going to measure the change in this thickness, or rather the breadth, so as to be more particular about it. So one can say that this is the length, this is the breadth, and this is your thickness, one can say. So we measure the change in the breadth due to the elongation. Now this is something we don't need any interferometer method for this. You can directly observe it using a microscope. So we simply placed a microscope, a lab microscope in front of this, and we made some markings out over here. And mind you, we got this idea after studying the video extensometer that we have done in the industry. We got this idea. And in the same way, instead of using a spray, what we did was we simply marked this, and this length is of course 1 centimeter, and then using the microscope we tried to find out by how much it has compressed, because in this particular case it will compress as I am actually stretching it. Now let us look at it. So what I observe in this particular case is this, that what we have is your y is equal to, once again the same definition, your force upon area divided by, this is the force upon area divided by delta L upon L. Force is the amount of force that are actually, the weights that are actually attaching it to it. Now in this case we are actually having three kinds of, so this was the unstretched one, this is followed by another load which is nothing but the 20 grams wala, which is nothing but 0.02 kg, followed by 0.05 kg, and the last one followed by 0.07 kg. So these are the different loads to which we are actually subjecting this particular strip or this polymer strip of the glove material. And what we do is we measure what is the change in the, lateral thickness. So in this case the change in lateral thickness was 1.173, or rather 1.173 was the unstretched breadth of our polymer strip, and this was, when I loaded it, it changed to 1.09 and went on to 0.694 for a load of 70 grams. So this was the lateral thickness that I have measured with the help of the microscope, and corresponding to that we are also having the axial length. So in the first case it was 7.8, the unstretched one, and the 20.1 was the last length, that is the most stretched, that was found whenever the load was around 70 grams. And from this we calculated the force and the area of cross section. Now in this case there was a catch, because we, in order to find out this area of cross section out over here, we do not know the thickness out over here. So the thickness we took it from our previous study that we have got from the optical interferometer method, and it is that particular value that we utilized out over here, which is the average of the two values. And that let me go back to the previous slide. So one can say that we took the average of 253 micron and 114 micron. That is the value that we actually took for the thickness, because I know this I need to know this in order to find out this particular cross-sectional area to which the force is being subjected to. So with the help of this, these values out over here, I know delta L upon L, and mind you students that always there were three different values that we obtained. So the first value was the extension for 20 grams minus the original extension, once again followed by the extension for 50 grams minus the original extension, and minus the extension for 70 grams minus the original extension, and the extension I mean both in the breadth wise and in the length wise, and mind you both of them are actually lateral in this case. But for my Young's modulus, I need only the axial one out over here, and I will have three values of y in such cases, and the value of the average value of y reported was, this is turning out to be around 3.33 into 10 raised to minus 4 GPa. Now mind you, this particular value out over here, the order of magnitude of this exactly coincides with what we have obtained in the previous case, this way. Now remains the question of finding out your Poisson's ratio. So your Poisson's ratio, as we know this, is equal to delta T upon T. So in this case also, it is the same K. It is delta T upon T, right? Delta T upon T divided by delta L upon L, and we already have a negative sign out over here. And since your delta L in this case is actually negative, this will ultimately give you a positive value, and this, the average in this particular case, comes out to be plus 0.29. So that is basically your Poisson's ratio. So we have obtained the value of y, that is the Young's modulus, and the value of your nu, which is nothing but your Poisson's ratio, using the microscope extensometer method. Both of these are our lab methods. Now let us move on to the last one, that is nothing but the standard values that we have got from the company, that is nothing but using a video extensometer. So students, up till now we have actually found out the Young's modulus and the value of the Poisson's ratio using the optical interferometer and using the microscope extensometer. Now the last thing that we are going to do is nothing but the video extensometer. That is the one which we actually got from a company lab. The values that are produced out over here are from this lab, and then we are comparing this particular values with those which we have obtained. So the values, before going to this particular values, let us see the plot that has been done over here. So here we see a graph of the force. There is a sensor placed out over it. So for example, let us say I am stretching this particular sample, so there is a sensor that is placed over there, and that directly gives you the force value to which you are subjecting the particular sample, and the extension in millimeter that is given by the video that is actually being focused on the particular sample. Mind you, we are actually taking the breadth change, the change in the breadth in this case. So the value over here, you will see that actually there are two plots. So this is nothing but the force which is there. We are having the force out over here in this region, and here in this particular axis we are nothing but having the position, or rather the extension of it. And we are having in this case two plots over here. This is one plot, this is for one particular sample, and this is for another sample out over here, or rather the sample in this particular case was the same, but we actually took the readings twice. And the value that we got for this was, there is a value of y that we got turned out to be 0.00098 GPa. So this compares well, at least in terms of the order of magnitude, with the values that we are actually obtained by other methods. That is by using the optical interferometer method and by using the microscope extensometer method. So here are the final conclusions. The value of y that has been obtained by the three different methods is, by the first method, that is using the optical interferometer, it is 6.62 into 10 raised to minus 4 GPa. That obtained by the microscope extensometer, it is 3.33 33 into 10 raised to minus 4 GPa, and that obtained by the last one, that is nothing but the video extensometer. It was 9.88 into 10 raised to minus 4 GPa. So at least one can say that using our rudimentary methods, the values matched well in terms of the order of magnitude. At the same time, the value of the Poisson's ratio turned out to be plus 0.488 using the optical interferometer method, and that by using the microscope extensometer method, we are getting a value of around 0.29. Unfortunately, we could not get any value, any substantial or rather an experimental verifying value with the help of the video extensometer. It gave us the value of y, but it actually failed to give us the value of nu. It actually gave a value of 0, which of course is invalid in this particular case. Lastly, we would like to acknowledge the help and also to these particular authors whose actually they have done a similar study, and when we compare our readings with them, you can actually find out that when we see the value out over here, which is nothing but the value of the Young's modulus, it turns out to be in MPa. That is, our values are, let us say, let me take the one value which is equal to 9.8 into 10 raised to minus 4 GPa, right, which actually turns out to be around 0.98 so much megapascal. So these values actually, this order of magnitude is actually match very well with what is actually given, what is actually found by studies who are actually done some studies on the similar material of gloves. So here also our values which are there are matching with the help of the literature values. So as you can see, this was a very simple PBL project that we actually, a very simple concept of interferometry that we learned in the SEM 1 practicals, and this was actually extended to find out the thickness of a paper in the lab case and then finding out the thickness of this glove both in the stretched case as well as the unstretched case. So as you can see, a very simple idea can actually go a very long way, students. And of course, I will like to take this opportunity to thank the particular students who worked rigorously and very meticulously in order to bring about this whole ideas in the form of an abstract and presenting it at ICFM, that is the International Conference on Functional Materials 2020, that is being held at IIT Kharagpur from the 6th to 8th of Jan. And these students are, first of all, Abin Thomas, followed by Pavitra Kumar, Prasanna Bansode, Rahul Krishnan, Siddhant Tambe, and ultimately it is me, their guide. So this is how you can see, students, that research can ultimately, it can go a very long way. A very small step taken right now can go a very long way, and you do not know when it will actually get converted into a giant leap. Last but not the least, I would like to thank the following people who helped us rigorously round the clock in order to see that all these ideas are actually being concretized and placed in the form of a paper. And these are, first of all, our beloved principal, Sir Dr. Sandeep Joshi, then followed by the Applied Science HOD, Professor Arun Pillai, and our R&D head, Research and Development head, Professor P. Goel sir. And last but not the least, the company that actually gave us the tested our samples for the Y values, and that is nothing but Fine Finish Organics Private Limited, MIDC, Taloja. So this is this, we end up out over here. Thanks a lot for watching this particular video.